Hi, in this video, I'm going to talk about the association between two nominal data, okay? In the last videos, we discussed about the association between the two quantitative data with nice quantitative data, I would say, no outliers, normally distributed, and so on. So in that case, we were talking about the Pearson's correlation coefficient and then hypothesis testing, right? And then next we did if there are outliers or not normally distributed, or if there are ordinal data. Then we did the Spearman's correlation coefficient, rank correlation coefficient, right? Rank based, that was the non-parametric test, and that was rank based measure of association. So next what we want to do is we want to do the association between the nominal data. If both of the data sets are nominal or the names, okay, then how do we do that? So there are many methods you can apply to test the association between two categorical variables. Chi-square test of independence is the simplest test of association between two categorical variables, nominal and nominal, or nominal and ordinal. Okay, we form a contingency table with labels of one variable along row and labels of another variable along columns. In the following example, 14 data are presented for the presence of plant disease and presence of certain insect. Does the plant disease is depend on or associated with the presence of the insect or not? That's what we want to test. Look at this. So presence of plant disease, that's the column. So there are 14 plants and they are testing if there are certain disease or not, or and then if they are in on that plant, if there are certain insect present or not. So present of plant disease, the first plant has plant disease present and the insect also present of insect. Okay, second one also has plant disease and insect both present. Third one has both no. Fourth one has no plant disease but there is insect. Fifth one both as. Sixth one no plant disease but there is insect, and no and so on. Okay, so what we need to do first here is to find out the chi-square. You need to do observed minus expected square divided by expected, right? But before that we want to find out the table for that, right? How do I do that? So you need to do in R, you need to do table and then PPD and then comma PI, right? But here what is happening here is there are four no, right? 1 2 3 4 no. There are no yes. How many are no yes? It says 4 again. Let's see, no yes, 1 2 3 and then 4, right? And how many yes no? This is the yes no is 0. There is none of them are yes no, and then there are yes were 6. So we want to check if, because you see that there is 4 and 6. 4 were no, if there is no plant disease, no insect, and 6 where there are plant disease and there are insect present. Okay, so are they associated or not? Meaning that if the presence of plant disease has presence of insect, or presence of insect has presence of plant disease or not. That's what you wanted to test here. Okay, so the chi-square, so to find out the chi-square, we do the observed minus expected square divided by the sum of that and divided by expected, right? So we need to find out the observed and expected for each of those, and then you do that. And p value, so p is less than alpha means there is no association. The above method only tells if there is an association. So you can do the you can measure the association between or the independence and dependence of one versus the other by using that method. We did that already, right? But this method only tells you whether there is a dependence or independence, but it doesn't tells you whether there is a positive dependence or non-positive or negative dependence, right? That's what it says. The above method only tells you if there is an association excuse me, a dependence or not, but it does not talk about the nature, positive or negative, or degree or strength of association. Also, as the sample size changes, the value of the chi-square may change. Okay, several modification has been proposed for that. Finding phi equals to under the root chi-square over n. You find out chi-square and then divide by n. Okay, with values phi close to 0 means weaker association. Another method is finding contingency coefficient C given by under the root chi-square over n plus chi-square. Chi-square is the same value there. And another 8 modification, probably the most preferred, is the Kramer's V given by V equals to chi-square over n times t under the root, where t is the smaller of r minus 1 and then c minus 1. Number of row minus 1 and number of column minus 1, the smaller of that. If both n equals to if n equals to t equals to 2, then v is same as the phi, okay, if n and 2 are equal to each other. Okay, so let us look at and also the v lies between 0 and 1 always. Close to 0 is weaker association, and whereas the close to 1 is the stronger association. Okay, so this is one method. I think I have done that here. Look at that. PPD is so C. So PPD is, so first one I did yes, and then I copied that first column, right? And then PI, presence of insect, I did that, and then I put the data in the column format, PPD and PI. Okay, if I so if I put the table of that, this is what you get, right? So how many were no, and how many were no, yes, no, and then yes. And if you do the chi-square correctness equals to false, what do you get is you got that p-value is 0.04. That means the p-value is less than alpha here, right? Oh, I said greater than. So so p-value here is less than alpha. So less than alpha, meaning that there is dependence. There is dependence or association between those two, meaning that if there is a insect present, then plant disease is present. That's what you can say here. Okay. All right. So this is what you get here. So the next thing, so you can find out basically because you know that it says only there is association or not, right? But if you want to find out, the values of the Cramer's V, how would that be? Cramer's V is equals to Cramer's V is is equals to square root, right? What you do is chi-square. So chi-squared is 4.2 divided by what is n? So n is the number of rows, right? And then t is the smaller of number of row and number of, so the smaller of r minus 1 c minus. There are n is the, basically let me find out what is n in this problem. Okay, so n is the number of pairs here. So n is the number of pairs or number of the sample size. Okay, so number of pairs or number of sample size, how many are there? There are 14. So there will be 14 times t is the smaller of r minus 1 c minus 1. So how many rows are here in here? Okay, so there are 2 rows and 2 columns. So that is n is that should not be n, that should be r. Okay, this should be r. All right, so this is not n, this should be r. Okay, so if r is equals to t is equals to 2, then v is equals to 5, because you see that you will have just t will be 2 minus 1, because see, if r is 2, that will be 2 minus 1, and then c is 2 minus 1, so that will be 1 smaller of 1 is just 1, so that will just become phi there. That's what it is saying here. Okay, so how much is that? 14 times 1, right? If you do that, what do you get? You get Cramer's V. Let me plot that. You get Cramer's V is equals to 0.54, right? So you see that there is an association, not perfect association, but there is some association, right? Because if the Cramer's V is close to 0, there is no association. Close to 1 is strong association, but this is 0.05, right? So it is, you can say, medium type of association there. Okay, that's what we can say. Okay, so the next thing we want to do is the measuring the agreement. What do you mean by the agreement? When 2 raters or observers are assessing some clinical characteristics in a number of patients, you may be interested in if the degrees of agreement of 2 raters, called the inter-rater agreement. Okay. Also, when a single rater is assessing the same subjects repeatedly of some characteristics in a number of patients, the degree of agreement is called intra-rater agreement. To measure inter-rater agreement, the simplest method, inter means between the raters, okay, between the observers. The simplest method is find the percent agreement, defined as the percentage of the agreement out of the total data. So what do you mean by what is the definition of percent agreement? Is the defined as the percentage of the agreement out of the total data. For example, out of the 10 data, if two raters rates 8 of them the same, then the percentage of agreement is 80%, right? Because if two of the so out of the 10 patients, if both of the both of the raters or both of the observers, if they rate 8 patients the same by both of the raters and 2 different, then that is the 80% of the agreement, right? This means 20% of the data collected in the study is erroneous, okay? In case of more than 2 raters, we calculate the percentage of an agreement for each row, then find the average of the agreement. You see that? Look at this one here. So how many are there? 1, 2, 3, 4, 5 of the raters. There are 5 raters, okay? And then there are how many subjects they are rating? 1, 2. There are 10 subjects they are rating. There are 5 raters to say the 10 subjects, okay? So they are rating either 1 or 0. You see that? If all of the row are 1, you just write down 1. See, average of those row. For each row you find out the average. 1, 2, 3, 4, 5, 1. So 1 plus 1 plus 5 divided by 5 is 1. Like that. See, here, if there is 0, so 1, 2, 3, 4, 5. There are 5 raters, 5 observers. The sum is 4. 4 divided by 5. You just find out the average of each row. This is what you get. Now you find out the average of that average, okay? 1 plus 1 plus 1 plus 0.8 plus 0.8 plus 1 plus, and so on, and divide by 10. This is where you get 90%. It is the study inter-rater reliability is 90%, okay? This is what is case. Of each row, then find the average of the agreement column. You find out the average of the agreement column after you find out the average of each row. This is how you measure the agreement, okay? So Cohen's Kappa, this is the notation for Kappa, is the robust statistic useful to either useful for either inter-rater or intra-rater, means between rater or within rater. So between rater means the many observers or many raters are observing many patients or many subjects and then rating. Intra-rater means same observer or same rater is observing many times, okay? So that's what it says. So inter-rater and intra-rater reliability. Testing Kappa lesser equals 0 is no agreement. If Kappa is between 0 and 0.2, poor agreement. 0.21 through 0.4, fair agreement. 0.41 through 0.6, moderate, and 0.61 through 0.8, good, and 0.81 through 1 is the very good agreement. But how do you find out the Kappa? To find out the Kappa, the formula is probability of A minus probability of E, or the proportion of agreement minus proportion of erroneous over 1 minus proportion of E. Okay, so basically proportion of expected, not the this is agreed and then expected. Okay, so proportion of the observed agreement minus proportion of the expected agreement divided by 1 minus proportion of the expected agreement. But how do I find out? PRE is given by CM1 times RM1 divided by N plus CM2 times RM2 divided by N divided by whole divided by N, where CMI, RMI are the column of row sums and column sums. So column sums, row sums divided by N, column sums of the second rater times row sums of the second rater divided by N, and whole divided by N. Okay, we'll see one example. N is the total number of observations. Okay, so here PRA is the proportion of observed agreement. Okay, that means sum of the agreement divided by N. That's how we find out here. Okay, so see, example is 2 raters observe 10 patients to check if they have the certain mental illness. So 2 of the observers are checking the 10 patients, and they want to assess for the certain mental illness. The results are given below. These are the patients 1, 2, 3, 4 through 10, and the rater 1 say yes, yes, no, yes for these patients. So you see that patient 1, both of them say yes, they have the mental illness. Patient 2, the first one say yes, second say no. Patient 3, first one say no, second say no, and so on. Now you want to make the table for that, right? So you see that, look at this here, I'm copying the same thing. Okay, if you do the table, you get that 3 of them say no, no. Okay, 4 of them say yes, yes. 4 of the patients, both of the raters say yes. 3 of them, both of the raters say no, and 1 one of them say, the first rater say no, second rater say yes. For the two of the patients, first rater say yes, second rater say no. That's what we got. And if I know the column sum and row sum here, you see that 3 plus 1 is 4, 2 plus 4 is 6, 3 plus 2 is 5, 1 plus 4 is 5. Now, what is n? N is 10 because the total number of patients, there are 10. CM1 is 5, CM2 is 5. You see that? With the column of the first rater, the first column, the sum of the first column, sum of the second column. I'm sorry about mentioning two, that the CM1 is the sum of the first column, RM1 is the sum of the first row, CM2 is the sum of the second column, and RM2 is the sum of the second row. Okay, that's what we do here. RM1 equals to 4, RM2 equals to 6. So as the sum of the number of no and SS is 7. So no is 3, SS is 4, right? You see that? So that is the both agreed. That is the no and SS are both of the rater agreed. That is the total sum is 7. That's what it says. PRA is the proportion of the observed agreement given by that sum of the agreement 7 divided by the total is 10. So 0.7. So 70% are agreement, right? So what is the PRE? How do I find out the PRE? PRE is CM1 times RM1. CM1 is 5, RM1 is 4. 5 times 4. 5 times 4 divided by 10, right? That is 20 divided by 10. So plus, so what is the second one? CM2, column sum 2. 5 times row sum 2 is 6. RM2 is row, second row sum is 6. 5 times 6 divided by 10. That is 30 by 10. Whole divided by 10. How much is that? 20 by 10 is 2. 30 by 10 is 3. 2 plus 3 divided by 10 is 5 over 10. That is 0.5, 50%. So kappa is, use that formula. Kappa is PRA is 0.7 minus 0.5 over 1 minus 0.5. So that is just 40% or 0.40. What can you say about that? Note that the percentage agreement between the raters were 70%, right? But the Cohen's kappa is 40%. So it is a fair agreement. We would say fair agreement between the two raters. Okay, that's how we find out. The standard error of kappa is defined by SEK equals to PA times 1 minus PA over N times 1 minus PE square. That's the standard error formula. Okay, and 95% confidence interval will be kappa minus SEK. SEK is that value, kappa is that value, plus kappa plus SEK, where PA and PE are the proportion of the observed and expected agreement. Okay, so SEK depends on N. You see that there is N here. So larger N implies the smaller SEK, and so narrower confidence interval. Usually N greater equals 30 produced good results. Smaller sample size implies wide confidence interval, and reduce includes 0, meaning no agreement. Okay, if you find out the 95% confidence interval for this one, what you get is kappa minus SEK. Kappa plus SEK will give you negative 0.17 comma 0.97. So it includes 0, right? That means no agreement. The reason is because the sample size was too small here. Whenever sample size is big, then you will get this value big, this value is small. Okay, as a result the confidence interval will have the smaller width. Okay guys, so this is how we measure the agreement using the Cohen's kappa. This is the statistical method. But if you do that agreement by this method or that method, this method, then it is not a statistical. Okay, but this one is the statistical method to measure the agreement between the two or more observers or raters. Okay, in the next video we'll discuss about the regression analysis. All right, thank you guys.